Okay, so now what we have here is we have some problems that you're going to find in Khan Academy under central, inscribed, and circumscribed angles. So what we're given here is that line AC is tangent to this circle O at point C. What does that tell us? That tells us this is a 90-degree angle right here. And what that means, we can use triangle sum theorem so that we know that there's 180 degrees total inside here. Well, if this is 90, then these other two must equal 90. Aha, very, very important to know. These two have to be complementary. So this is a pretty simple problem to solve. 90 minus 63 equals, and that would be 27. So that'll be our answer there. 27 degrees. Okay, next problem here. You remember me talking about that when tangent lines form a quadrilateral with the center of the circle and the circumscribed angle, because this is, let me sketch this out for us here. What we have here, so what we have here is we have 90-degree angle because this is tangent at the point of tangent. See the tangent line and the radius of the point of tangency, 90 degrees. And here's another 90 degrees, so that's 180, and the quadrilateral must be 360, so these two are supplementary. They must equal 180. So we have 180 and minus 92. That's a 0, not drawn very well there. It's not a 6, it's a 0. And we're going to get 88. So that's 88 degrees. Okay, let's go ahead and put 88 in there. Next, okay. Angle C is inscribed. Okay, let's work on this one here. So now, if it's inscribed, we notice this chord right here starts at A, goes through the center O, ends at B. This is a special chord, and it's called a diameter, right? Okay, so now we're going to think about this. The diameter is a central angle, AOB, that measures, well, the arc here is a semicircle. So the central angle has to measure 180 degrees, right? Because that is half of a circle. Just like over here, we have 180 degrees because that's the other half of the circle, right? So it's a diameter. A diameter cuts the circle into two halves, so we call them semicircles. They're not arcs, not a major and minor arc, two semicircles. What do we know? Well, we see also that this central angle that measures 180 degrees, let me get the color, has an inscribed angle, right? ACB is the inscribed angle, and we have to remember the relationship. This angle is half as much as that angle is, right? Or we'd say that that angle is 2 times as much as the inscribed angle is. So the central angle and the inscribed angle have that relationship. The inscribed angle is half as much as the central angle. So that means this is a 90-degree angle. Now we're cooking. And this is, you might remember this if you took Geometry A with me. You might remember, hey, we talked about the right angle machine I built, and how when you checked out all the right angles that existed for a given hypotenuse or diameter, they formed a circle, right? They formed, well, here's a half a circle, and then you could go around the other way and you'd have a full circle, semicircle and a full circle. So we knew that this was a right triangle to begin with. So this should have been a right angle. We know that's 90. So now we have that these two angles have to equal 90 together. They're complementary. So we'd have 90 minus 60. We take away 60, and the other angle must equal 30. Okay? 30 degrees. Okay, how about this one? Okay, now we have this problem. We remember this is a 90 and this is a 90. So we have a quadrilateral. Looks a little like a kite here. And we have 110 degrees on this side. These two have to equal 180. So this guy has to be 180 minus 110, or 70. So that's a 70-degree angle. Okay, now we have a length problem. All right, this is going to be pretty good here. A length problem. We know that this leg, first of all, we know if these lines, this is tangent to the radius at point C, then this is a 90-degree angle. So now we have a leg. This is a right triangle, isn't it? Leg, leg, and a hypotenuse. Okay? So now we're asked to find the length of AC, which is one of the legs here. Well, what do we know about the hypotenuse? The hypotenuse has, this portion of the hypotenuse is 2, the other portion is 3, just like it is here. See? It's the radius, so it's going to, OB has to be the same as OC. So OA, our hypotenuse, has to measure 5. So here we are. How big would AC be? Well, we would use Pythagorean Theorem. Leg squared plus leg squared equals hypotenuse squared, right? Hypotenuse squared. Okay, so our one leg is 3, so 3 squared plus the hypotenuse squared. Oops, plus the leg squared, rather, is equal to the hypotenuse. Oh, the hypotenuse is 5, so we could write 5 squared. That's ugly, but it'll work. We have 9, that's 3 squared, plus the leg squared is equal to, what's 5 squared? That's 25. So we subtract 9 from both sides, and we get that the leg squared is equal to 16. And if we take the square root of that, we get the leg is equal to 4. So this leg would have to be equal to 4. Try to remember that too, by the way. 3, 4, 5 is a special triangle. It kind of comes up a lot in these problems. If one leg is 3 and the hypotenuse is 5, then the other leg is going to be 4. And 3 and 4 always go with hypotenuse of 5. And that's true for multiples of it. So 6, 8, 10. Take every number by times 2, then it'll still be true. 6, 8, and 10. If we multiply by 3, we get 9, 12, and 15. So this is just a good one to know. Anyway, in this case, our answer here is going to be 4. So let's put it in. And that's how these problems are done.